Hi, everybody. So how's the conference so far? Kind of lame. How's the conference so far? All right, so I'm going to actually start by talking a little bit about my background. Since we're in New England, I thought it would be very useful to talk about where I actually started studying, which was at the University of Rhode Island. I was studying things like this, and my New Englanders know this is a tick, exactly, and specifically what kind of tick? The tick that can give you Lyme disease, exactly. We're in Connecticut, which is where that name comes from, so really important. So this is what I actually used to study. I was really interested in parasitic disease and transmissions to humans, and I was studying at things like this under a microscope. But I started realizing that I was actually more interested in using computers than I was interested in using microscopes. So I went into into computer science essentially, so that I could use data to tell stories about science. And that eventually brought me here working for NASA's Chandra Observatory. So I actually just celebrated my 20th anniversary working at Chandra. Thank you. I'm excited about this. I'm really like, how did that happen? But it's been good. So how many of you have heard about the Chandra Observatory before? Okay, great, awesome. So you know that Chandra is NASA's premier X-ray observatory. Chandra looks at some really amazing things, black holes, exploding stars, things like colliding galaxies, all sorts of really amazing things. So I've been lucky enough to work on NASA data for almost 20 years now. Chandra's going to celebrate its 20th anniversary next year. So we're actually looking forward to doing quite a few new exciting things for that. But for me, I think it was really interesting going from studying spiral-shaped bacteria, like this one. This is the spirochete that you find inside the stomach of the tick that can, when transmitted to humans, cause Lyme disease, to spiral-shaped galaxies, right? Now, there's actually some similarities when you're working on those different kinds of data. First, they're all sort of invisible to the human eye, at least at a natural level. You have to use a microscope to look at the former, and obviously a telescope to look at the latter. But there are also other similarities I thought it would be fun just to take a quick look at. I hope the contrast is okay. But this is a little game for anybody who can see it. I think it's a little tough for you guys to see it. But essentially, these are pairs of images that I've selected that are either really small or really big. So we're going to have a quick game. For those who are paying attention, let's look at this bottom pair right here. Who can tell me which is micro and which is macro, that bottom left corner? So, go ahead. Which one? The one on the left. Yes, exactly. That is a microscopic piece of the retina. And then on the right is a supernova, photostar SN1006. You can see there's actually a lot of similarities just with texture, but also with color. And even because of the microscopic lens with a little bit of shape. So there's a very similar visual language that occurs between working with images on the micro level and working with them on the macro level. Let's try this middle left column right here. Out of the two yellow images, which one's micro? Left is macro. Yep, and that would be our exactly. And then the right image is, and I did not work on this one. I think the right image is a bit of onion. So let's do one more here. On the upper right, the two on the upper right, which one's micro, which one's macro? I think you guys will all be able to get this one. So, which one's macro? The far right? That one right there? Yep, and that is. So what's the image on the left? It's actually rabbit tongue. Yeah. So, but it was really interesting to see the similar color and striations in those two images and how interesting they were to compare. Actually, let's do one more. How about this one down here? I think you can all get this one too. Which one's macro? Macro, macro, macro. Right? And what's the image on the left?
2M12.
What is it?
It's 2M12.
2M12. So this is jet 3C273 on the right, and this is actually like cells forming, cells like breaking apart. So again, there's a lot of similarities. The colors of these two images are almost exact. So it's really interesting for me to be able to look at data like this and see the similarities in the way that it's processed, the way that it's colored, the way that it's viewed. But I don't spend my days looking at anything under the microscope anymore. I haven't looked at a microscope directly in 2 decades. Instead, I get to look at images like this. So usually when I'm talking to a group and I'm trying to introduce the topic of what the Chandra Observatory does, I always have to start here. And this image is of our, I like an interactive presentation in case you can't tell. So otherwise I'm afraid you guys are going to fall asleep. So let's just keep it interactive. So yeah, exactly. So this image of our sun is one of my favorites. It's from NASA's Solar Dynamics Observatory, and it shows all the different kinds of light that SDO gets to look at our sun. And it's really beautiful because I think it shows quite well why we need different kinds of light in order to study even just one very special object. So when I'm talking about the electromagnetic spectrum, I usually start by making it a little bit more relevant to people's lives. It really is important to grab people where they are. So when I'm talking about like the EMS, I might start talking to, especially with kids, what kind of light are you familiar with? So they might not think of any kinds of light at first besides what they see. A light bulb is usually one of the first things that a kid might think of. So then I'll be like, well, do you use a microwave? How many here use a microwave? I'm assuming most of us. I mean, I know I use it a lot. So when you're using a microwave, you're using microwave light to disturb the water molecules of your food to heat it up faster, so that macaroni and cheese gets warm in no time at all. And if you've ever gone to the doctor or the dentist, you've gotten an X-ray. If you're ever using a remote control or one of those automatic soap dispenser, you're using infrared light. If you're a fan of comic books and you like the Hulk, maybe you know a little bit about cameras. Who knows? But the point is, it's really important to ground people where they are. And I like to talk about why we care about different kinds of light as well. Obviously, I've spent pretty much my whole career using different kinds of light that we can't see, mostly X-ray light. So why would we care about studying different kinds of light? I like to use the analogy of the baseball field, and I am like the least sporty person ever. So it's perhaps a little ironic that I use this analogy, but I just really like the visual of it. So, if you are going to a baseball game, and this is all you can see of the field, how hard is it going to be to understand what the Red Sox, I'm assuming we're still Red Sox fans over here, or maybe we're Yankee fans, well, maybe there's a mix, but, so how hard is it going to be if this is all you can see of the playing field to understand what your favorite team, be it Red Sox or Yankees, or wait, what team are New York team? The Mets. I figured there were some Mets fans here, all right. So how hard is it to understand what's going on in the game if all you can see is just this? What's this? Just a sliver down the foul line, down third base, right? How difficult is it for you to understand what's going on? Sports fans over here. Pretty hard, right? You do not know how many players are on the field. You do not know what the pitcher's doing. If you don't have any familiarity with the game, you don't even know that there is a pitcher, right? So it's really hard to understand what's going on when you have such a limited perspective of the playing field. And the analogy is, if we could only see with the type of light that our eyes can detect and at that intensity level, this would be like our universe would be limited to. We'd only get to see a sliver of the universe, and we'd really be missing out on all the amazing plays going on in that universe. As soon as you can see the entire ballpark, and I think a friend of mine took this, and I forget where, it's not from here. Might be Baltimore? Anyways, once you can see the entire field, yeah? Okay, good. Then you have a much better chance of understanding the rules of the game. Now, granted, there are still going to be lots of mysteries to figure out, just like to me, there are baseball. But you have a better chance. Sometimes I like to use a musical analogy too. So if there are any people here who play piano, you usually are, okay, awesome. Oh, a few, great. I don't play piano either, but I still love this analogy. Again, if we could only see the type of light that our eyes can detect, it would be middle C and a few keys around it, and that would be it. So how good would your favorite piece on the piano sound if you could only play middle C and a few keys around it? Pretty terrible? I mean, I don't think you could do much with just 3 keys on the piano. So the idea is being able to take these analogies, whether they're visual or by sounds or whatever, and try to help people understand why it is we need to look at many different kinds of light. I'm going to start talking about my favorite kind of object now. I like to talk about dead stars a lot because they're just so amazing and beautiful, and for me it's a bit of an origin story. So you're probably familiar with which object this is. Pop quiz, which object is this? Frank, you can't say. This is Cassiopeia A. So Cassiopeia A is one of my favorite objects because it was actually the first object that Chandra ever looked at. Well, it was Chandra's first flight. I think there was technically one little object that looked at very briefly before this. But this is not by Chandra, this is by the Hubble Space Telescope. We're looking at beautiful filamentary structure around the 10,000 degree mark. I love this image because it's just so simple and so elegant, and it really gets the point across this material disseminating the universe. But then as soon as you look at that same exact field of view in X-ray light, you get something that looks completely different. Now, when I'm working with different audiences and I have to communicate the difference in the type of light that we're using, how is it that you can, relate these two objects together? Starting with the optical always gives people sort of a connection point, right? Because this looks more like something you think of when you think of space. When you're looking at an image like this, if you didn't know it was space-based, it could be of any different scale, right? This could be something underneath the microscope. So the idea is to be able to connect and provide context. So often when we're making images from Chandra, we really do try to combine them with optical data, or sometimes infrared data, or other types of light, in order to help set that context. So when we add the Chandra data, now we're looking at material that's millions of degrees hot. You can talk about different things with that, and it's really wonderful. But what I really like to do is talk about how we get to that point of that image, because I think that's another thing that a lot of people don't understand, that these images are not just giant space selfies, right? They take work. They take work. And the idea of why that matters is something that we've been investigating for a while. So this is Cassiopeia A from Chandra again, but now we're looking at it just black and white. It's relatively raw, but here's a version of it even more raw that hasn't been processed at all. That's just one small exposure time. But really, I like to take people all the way back to this origin point, right? Now, why would I do that? Well, for me, 2 things. One, with my computer science background, I actually find it really interesting to kind of take people back to, this is the way we talk to spacecraft. This is what we use to talk to cell phones, to talk to computers, to talk to any number of machines. Why? Because it's a very simple system of ones and zeros, ons and offs. So the binary code that we use, we don't have to speak in binary code. It would take a really long time to say hi in this language. Never mind calculate millions of lines of ones and zeros for an image. But we use software, and we use software in order to decode that information and then translate it into the image, that visual representation of the object. Because again, I think it's really important to talk about the fact that these are not just perfect photos, snap and you're done. There are people underneath those images that are creating them, that are making choices based on their own scientific knowledge, based on their own aesthetic choices even, to make the image at the end. So when we get our table of data, it looks something like this. We've got the time, we've got the location in X and Y positions, we've got the energy, and it still doesn't look too exciting yet. It's kind of showing the bare bones of what our observation is looking like. We then translate that data with yet more software into the visual representation of the object. So we start to get something that looks like this. But we need to move on yet a step further after we've smoothed it, after we've scaled it, after we've cropped it, after we've removed artifacts. All those steps, all those decisions that are being made along the way. The last step for me is typically adding color. In this case, we've added color by energy cut. So the lowest energy X-rays are red, the medium green, and the highest energy X-rays are blue. So I like to tell people that the reason we do this is, one, this material is invisible, so we can't see it anyway. We have to do this kind of processing in order to understand it visually. And then by adding color, you're adding more information. You're adding to the informational quotient of that image. Because you can clearly see when you're looking at an image that's been color-coded like this, that expanding shock around the perimeter, that's the highest energy material. And then you're seeing the red and green material are more kind of spread out and along through the jets. and that's the lower energy material. It gives you a more immediate visual cue as to what's going on. And people are used to these cues because on weather.com or on the nightly news, depending on what area you were born in, we're used to seeing things like a weather map that's color-coded by, say, temperature or by wind or precipitation. So we're used to processing that in a visual way with a color code. So one of the most important things we've actually found is that telling people what that color code is really, really, really critical. People really don't understand at first that these images are made. Once they find that out, sometimes there's like a loss of trust at first, and then it's really important to build that trust back up by being as absolutely transparent as possible as to what it is that you're doing with this data and why. So there are other ways to hack apart the data. I mean, if you're working on something like Mars, you're going to be doing something by topography. If you're working on something like a supernova remnant, you can do by the chemical emissions. So in this case, we have a version that's color-coded red to the silicon, yellow to the sulfur, green to the calcium, purple to the iron, and then the remaining outer glass layer is in blue. And that gives you a different sense of this object, right? It gives you a different understanding of where things are, where those chemical elements have essentially distributed. And it's really interesting to be able to talk about that because Cas A particularly is a star that essentially turned itself inside out when it exploded. And you can trace that when you look at how the iron is more along the outer areas than the inner areas at this point. So even though the iron was the innermost part of the core before it exploded, it's now on the most outermost part of the remnant. So by being able to color code it, then you're able to see in a visual way what's going on in this remnant a little bit more quickly than if you had to read it in a paragraph or look through a graph. So with Chandra being up for almost 20 years, we really have an amazing set of data with Cassiopeia A. It's my favorite. I like to talk about it a lot because we have such great data. Cassiopeia A is about 10, 11,000 light years away. So to see it changing over time, like we are here, the first time I saw this movie, I was just absolutely excited. This is showing just 4 pops from 2000, 2002, 2004, and 2007, I think. And you can see it changing over time. And what I like about being able to show time-lapse data in astronomy is that it gets back to the whole idea that these are not single-space selfies, right? That these are objects that are dynamic and changing over time. So anytime that you can use data in order to show that these objects are changing and dynamic, it helps situate the viewer in a different way. In this case, by looking at how the data was changing over 2000, 2002, 2004, and 2007, I think, the scientist in this case was able to learn that the material is traveling around 11 million miles per hour. And that's just a number, right? But the first time you hear that number, if you're not familiar with exploding stars, it can be pretty interesting to understand that that's how quickly the universe changes. And when you have something like this that you can see changing over time, it's also useful to be able to talk about look back time and open up that discussion of essentially, I think astronomy is like the best time traveling job ever. I don't have to leave my desk, but I get to travel back in time. So simple. I don't watch Doctor Who, but what's that big blue box? Is it TARDIS? I knew you guys would know. I'm in the right audience for that question. So I don't even have to go in the TARDIS. I get to just sit at my desk. One additional thing we were able to do with this data, again by using different kinds of light, by using infrared light, optical light from some ground-based telescopes, and then also the X-ray data from Chandra. We worked with a scientist at MIT at the time, Tracy Delaney, who was understanding the velocity maps of this object specifically. And we had just stumbled upon some software called astronomical medicine, or AstroMed for short, Alyssa Goodman's group was working on at the time. And we convinced Tracy to be our guinea pig and work with us to get the data into this new 3D software application. Because at the time, there really wasn't a lot of great data-driven astronomy 3D software applications. But now we have a few options like Shape and others. At the time, we didn't. So she worked with us in order to get that data in a format that we could then understand in 3D. And this was the first time we were able to see Cassiopeia A in a 3-dimensional map using actual data. This is like the true data that was driving the story.
And in this case, it was nice because it was essentially the simple geometry about the object and the Doppler effect that we could derive all this information from. So when you're telling the story about 3D Cassiopeia A, you can tell a story about basic physics. I think is actually really exciting. But again, as this is an object that's 10, 11,000 light years away, being able to see, above it, around it, through it, and understand how it looks in 3 dimensions was, for me, just incredibly exciting. We took like a wire mesh of that data into a commercial package because the Astromed was pretty limited in visuals. And by taking that wire mesh into Maya 3D, we were able to create a version that you can see on the screen that's a little bit more astronomical looking. The original software from astronomical medicine was actually adopted from brain imaging scientists, so that's why it looks a little brain-like. But here we have a little more control of the colors and the textures and the timing and the positioning. And this is a pretty faithful representation of what Cassiopeia A looks like in 3D according to this nominal data we have. And it's really great to have the science that comes from this type of research as well. Scientists who make models of dead stars for a living actually learned from this 3D model. They learned about how the star explodes and how it comes off into different pieces first as that spherical piece, and then the stronger jets that come out after that are incredibly fast. So there have been, I think, 3 additional papers just on the 3D structure of Cassiopeia A since this release, and it's been really exciting to see how that's changed. But we were, I think, really interested to see what we could do with that information. So 3D on the screen is fine, and we have a version that you can manipulate and change colors, and that's all cool. But we really wanted to see what else we could do with it. So I had some friends down at the Smithsonian who were responsible for 3D scanning President Obama's head. And they set him up in a room, and they set up these cameras around him, and it was pretty cool. And they did a 3D bust of President Obama. And I'm like, well, since you guys did that, how about helping me 3D print a dead star? And they're like, yes, we will. So I learned from them how to create an STL file and how to do 3D printing, and our group has been working on that for a while, ever since. I have a couple versions here that I'll show you. When we're taking these out to work with our public, we've learned quite a few things. So we first started, I'll be honest, I first started thinking, oh, this will be fun. That's what I said. It'll be fun, she said. And it was fun, but 3D printing is, how many here use 3D printing at their museum or planetarium? So few of you. It's pretty complex, technically speaking. A lot can go wrong with a 3D printer. It can absolutely drive me nuts, but I really, really love the outcome because it gives a tactile form of this data that I've been working with for so long, and it's a way to provide an artifact for people to hold. And to be able to talk that, this is a star that exploded 10, 11,000 light years away from us. The scale of this thing is pretty monstrous. It's about, the surface area is about 40 billion times the surface area of our sun and planets. So when you talk about things like that, and then you let students or grown-ups handle the model, it's actually a pretty powerful experience. And I found it actually very impactful to see how people respond to those tactile models. But beyond that, when you start getting to specialized audiences for people who are blind and visually impaired, I know Noreen does a lot of work with those audiences, wonderful work. It's absolutely incredible to see how this can impact the way they understand the universe, because this data is very difficult to access otherwise, right? When you have a 3D model on a screen versus a 3D model that you can hold, it's absolutely amazing to see the difference. And we've learned a lot by working with the National Federation of the Blind on these 3D prints. We learned what size is better. This is actually a pretty good size right here, if not a little bit on the large size. How resolution has to be, the smoother the better, obviously. You'll see that this is cut in half. So we have magnets that attaches the two pieces together. And the reason it's cut in half is so people who are blind and visually impaired can explore all of the model. That is such a simple thing, and it is such a simple thing to do, just cutting in half, and we just never thought about it, right? It wasn't until we took this to the youth slam at the MFB and worked with students to see how this would be more useful to them that they said, cut it in half. like, yes, it was such an obvious aha thing. And that's made it really useful for people that have issues with their site. We also, do that in the clicker. I have some competition in the boat area apparently. We also learned how to do a special kind of powder printing, which was a little bit more expensive setup, in order to preserve the color information. Because again, with color here, the color has value. So the colors are the chemical emissions from this supernova remains. And you can see here, this is a very small version of a powder printed version that is also colorized. And another thing that we learned is that jets are very fragile. So using magnets in order to attach the jet. So this way, if the jet breaks from too much handling, all you have to reprint is the jet versus the entire model. The entire model can take like 2 days to print. So very slowly over time, we learned a lot of lessons with how we 3D print. And I'm going to pass these around. When you bring your daughter to work, and she can help you to be your assistant, that's the best. And you're there. Wait, and this one. Thanks, Anna. Now I'm embarrassed her. She'll never want to come with you to another science event ever again. Thanks, Cindy. All right, so we had this really cool model, and I was having a lot of fun with it. And I thought, well, what else can we do with this data? Because I am a data person. That's, again, my background. One day I walked into the Brown Virtual Reality Lab, and they had a data set from Mars, so you could essentially walk on Mount Sharp. And again, I've been in the field a while, but that moment was incredibly exciting to have a virtual reality experience on Mars. It just opened up the data to me in a very different way. So I asked them, would you like to work with me on getting this red star into virtual reality? And amazingly, they said yes. I feel like people don't know. When I ask something, like I mean it, and I'm like, I will be annoying. But they don't know that when they say yes. So the folks at Brown were really amazing to work with. They taught me a whole lot about virtual reality. How many of you work with virtual reality in your space so far? Okay, so a few, all right. I think there are a lot of people that are skeptic about virtual reality in general, and absolutely rightfully so. Virtual reality, I think, is still relatively new, and we don't quite understand how it will impact various audiences. It depends on the type of virtual reality you're using. When I went to Brown, the virtual reality cave fits about 10 people at a time. So it's actually like an interesting social version of virtual reality where you are seeing what the master is seeing essentially, and you have like the secondary headsets. And it's a very sort of social, interesting space to be. So the first time we were able to get Cassiopeia into that virtual reality space, in that social space, I was again absolutely flabbergasted. I saw things in the data that I had never noticed before, clumpiness I hadn't seen, like the underpinnings of it I hadn't quite understood in the same way. And this is a data set that I have been working on for 19 years. So to see things new at that point was really exciting for me. We have about 2 million seconds worth of data on Cassiopeia. So it's a very rich data set. To have these different kinds of outputs to be able to understand that data in a new way was just really amazing. But we wanted to make sure it was accessible, so we worked to create versions that were also useful in Oculus Rift. So we have that version now. That's also public domain, so if anybody's using Oculus Rift with their virtual reality experience, please do get in touch. We worked with the Smithsonian to do a version that is accessible via Google Cardboard, and also is interactive through this website. If you go to chandra.si.edu/VR, there's a link to this Smithsonian application, and you can change all the color values, you can move around the object, and really get a better sense of how it is that it works. We created our own version in Google Cardboard as well. All of these things are public and free, so if you are interested in starting to incorporate any type of VR in your programming, please do get in touch. But again, all of these versions that I showed you, they all came from the original data set, right? These are all different faces of one supernova remnant, and we're just looking at them in many different ways. But they all come from the same bits of binary code. It's just different ways of expressing them, different ways of visualizing them, different ways of understanding them, and different choices that are made along that way. I'm going to show you one more example, Supernova 1987A. So what are my favorite supernovas? I mean, who here has a favorite supernova? I think I'm in the right crowd to ask this question, right? All right, thank you. What's your favorite? That one, yes, that's right. This is the best. So Supernova 1987A is really beautiful. We just had the 30th anniversary recently, so we wanted to do something special with that. This is the image of the close-up area with ALMA radio, ALMA data, Hubble data, and Chandra data. We were working to understand Supernova 1987A in a more holistic sort of way. This short time-lapse movie is showing the Chandra data changing over time, and you're seeing the brightening of that ring. We worked with Sal Orlando, a scientist, I'm blanking where he's from, but he had this really cool model data that he had been working on that he constrains with the Chandra observation. So this is simulation data that's been made more correct essentially with the X-ray observations. And by doing that, he was able to create this visualization with Frank in order to see that ring brightening over time. Now, when you think of Supernova 1987A and you think of, go back. The X-ray data looks kind of plain. Oh, today's National Donut Day. This kind of looks like a donut, right? I mean, if you're so inclined to be like donuts, it's not that any of us do. It does not look super exciting, right? As soon as you look at that data in a 3D form, and understands that we are presented with just one view of this supernova remnant, and when you turn it to the side, you can see those beautiful filamentary structures sort of sticking out like little fingers, and it kind of looks like a crown. And I didn't bring this 3D model with me because it was raining so hard, and I didn't have enough bags to cover them all, so it's in my car. So unfortunately, I didn't get to bring it, but it actually looks like a crown when you 3D print it. And being able to see that data represented in a very different way, again, it was just a great learning opportunity. So this is the very first version that we had of the data before we went to 3D print it. And you can see there's a lot of data that's actually not connected. So one of the things that we had to do in order to 3D print it was to delete the data that's not connected, because when you 3D print it, it would just literally fall off, right? So to get one more example of choices that my team had to make in order to do a different kinds of data visualization. And here you can see a 3D print of that object in progress. You can see how beautiful it comes out. We're working on a couple of new objects. One of them is Tycho's supernova remnant. One of the scientists that we worked with here, Brian Williams from Goddard Space Flight Center, found or researched about 50 different velocity points for that object. So we were able to bring that into, it's not playing, hold on. So one of my former employees, who's now actually working with Frank, took this into Slicer and made a version that's essentially 3D-ish. So we don't have all the 3D data for this object, but we have some. So he was able to do this version where it looks like you're flying into it. But it's based on 50 different points that are definitely correct. So I think that was actually pretty exciting to see. So there are different collections of data, and different, that data has different qualities. So you're not going to get a perfect 3D model like we have with Cassiopeia A each time. And we're trying to understand what we can do when we have data that's only partial or not, quite perfect. But I really thought that came together quite well. We have a few other objects that we're working on too, but I think it's really exciting to be able to look at this data in that sort of holistic way. All right, yes, we can get a 2D image. Can we get something else? Can we get 2D changing over time? Can we get 3D? Can we make a 3D print? Can we bring it into virtual reality? And I mean, anytime you're talking about things like dead stars, you get to talk about our origin story essentially. So that's something I always like to be able to talk about when we show, especially the color model, and then who has the color version of Cassiopeia A. But when you're showing something that has that color data for where the iron is, where the calcium is, where the argon is, and you can talk about that link to humans and other possibilities for life, it's I think really exciting to do. I thought I would talk at the end of my talk just very briefly about some of the work we've done to understand how people look and perceive this astronomical data. And There are a number of different factors that differentiate both experts and non-experts in how they approach astrophysics data. So we're looking here at the bullet cluster, which is really lovely and famous and all that. But when we show this image to an expert, his or her first question is typically, all right, well, they know this object really well typically, but it might be, which telescopes are involved in this data set? What are the details of the science? What do the colors mean? How long was the observation time? The first questions are always very specific questions as to the science. Then, after staring at an image like this for a couple minutes, then the questions move to, well, that's pretty cool looking. No, that's not too bad. That's not too shabby. And they get to the beauty of the image second. So it's science to beauty. When we show this image to non-experts, it's completely reversed. It's, oh wow, how beautiful. Lovely. Eventually, if you sit with them for a little while, those questions start changing to, well, what is it? That's usually first. What do the colors mean? Or what is the scale? How far away? How big? Those scale questions. Scale is very, very high up on the list. So it's interesting to see that it's so split, but that wow factor is always first for the non-expert. And it's usually second for the expert. When we're looking at things like color, this is an image that we worked on with a couple. Gosh, I want to say it was like 2006 now. When we were first working on this image, this is a combination of X-ray data, optical data, and radio data. And it's the Centaurus cluster, so we were trying to tell the story about the supermassive black hole that's buried in that white spot, that's spewing out all this high energy material, and it's a really, superheated object. So we're kind of interested in talking about the story of that. The heat of the object is actually important in this case. But typically when we color X-ray images, we use like blues and purples. Why? Exactly. So with this object, this was the first version.
I didn't hear what she said.
Oh, just so the spectrum. So in physics, blue tends to be the most hot, right? So in physics, it's kind of the opposite of what the everyday person is. And the everyday person looks at the two faucets, and the one that's blue is going to be cold, and the one that's red is going to be hot. So if you're creating an image that's meant for a non-expert audience, and they're used to blue being cold and red being hot, and you want to talk about the heat of an object, do you color it red or do you color it blue? Who would color it red? Who would color it blue? So only like 3 of you coloring it. Who would color it red? For real, I really want to see. Who would color it red? Yes or no? Who would color it blue? All right, so it's kind of split. So most of your non-experts are going to understand the red is hot. If you want to talk about the heat of an object or the high energy material of that object, going with red gives them something to connect to faster. However, you can just as easily make it blue and talk about the physics, right? Why you would use blue. That's a choice that you're going to make. For what we found, aesthetically speaking, there was no difference. Experts and non-experts were split 50-50 down what they thought of this object, in a beautiful way. Is it pretty or is it not? 50-50 like the red versus the blue. Oops, okay. When it came to understanding, the non-expert had an easier time understanding the red. So though you can color it blue, you absolutely could and take that and use that as a learning experience and all of that. When you're sending an image out into the world, into the great wide internet, and you're not going to be there to talk with them all the time, having an object that speaks for itself could be more useful. When we look at issues like scale is absolutely the biggest question people have. It's really amazing how many questions on scale, on magnitude, will come up, and how many misconceptions there are. What everybody clamors for, both experts and non-experts, are the scale comparisons. So having a scale like this, when you have the sun and you have just, a small earth that you can show up, very, very effective, wonderfully effective. As soon as you go to a bigger object, like this, where it's a cluster of galaxies, it's very difficult to do. But even if you can somehow get into words the size and magnitude of an object like this, it will help the non-expert tremendously, and the expert as well. So scale is really important. Now, why do I have this strange lady on my screen? So what I like to talk about is context, essentially. And any art aficionados here? Any really into art? I know you're a space crowd, but I like art too. All right, so if I was in a gallery and there were 1,000 different portraits to look at, and I was walking down the corridor and I saw this portrait, would I stop? No, I wouldn't honestly. I don't know a lot about art. I love art, but I don't know a lot about it, art theory and all that. I don't know any of that stuff. Art history, not my strong point. So if I saw this image of this lady in this frilly white cap, it would not necessarily arrest me, right? However, I have some friends of mine who are art historians, essentially, and they told me the story about what this image is. And I'm going to step over here for a second because I actually have a quote that I want to read. So this is from Madame Henri Francois Raisonnet, excuse my French, it's been years. This was done by artist Eugène Delacroix, 1835, oil on canvas. Now, she was apparently his aunt by marriage, but they were very close, this woman and the artist. And in her earlier years, she was known for her beauty. 30 years before the date of this portrait was taken, she actually served as a lady-in-waiting to Empress Josephine. And when she came back from that, I guess she spent a lot of time hanging out with her nephew, and they had a lot of laughs. So after she died, Delacroix wrote to his friend Georges Sand that each of the beings necessary to our existence who disappears takes away with him a whole world of feelings that no other relationship can revive. Now, if I want someone to write something about me when I'm gone, that's kind of what I want to hear, right? I mean, that's a really nice sentiment for someone to write in a letter to a kind of famous person, Georges Sand. So understanding the context of this portrait, that this woman had this crazy past, hanging out with the Empress, cheating with Napoleon, hanging out with really cool writers and painters. She was in the middle of some of those salon days, right? She had a wild life, and this painting expresses that sort of frank tenderness that her nephew had for her. If I knew that, I would stop and I would look at it. Why am I talking about this? That was a long story to essentially say that context is still king. Our research has shown very clearly that you can look at an image like this and understand its beauty, absolutely. The aesthetics are great, but as soon as you understand the context, as soon as you provide some sort of link to tell the story about that data, you will not only help people understand the data more, you will actually also increase the aesthetic appreciation of that image. So when we're talking about this image and we just say, this is an image of Saturn, there's some ultraviolet data, the name, the rank, the serial number, that kind of tombstone data, right? Well, that will tell the person what they need to know, sure. But that will not necessarily change comprehension or aesthetic enjoyment. As soon as you talk about the story of this image, you can talk about it a few different ways. You can talk about Saturn's rings. In our testing, we actually talked about, you can't see it because of the contrast, but around 10 o'clock, there is a little blue pixel, and that blue pixel is Earth. And as soon as you talk about, essentially Earth is in this image and why all that's important, the aesthetic enjoyment of this image goes up at least 50%. In some cases, it goes up as high as 100%. It's a really big difference to see. So being able to talk about the context of this information by using storytelling, not just boiling it down to the data, has been really helpful for us to learn. So for fun, I write books about stuff like this when I'm not hanging out with my girl and my son is not here. All the stuff that I talked about, there's a few URLs on the website. Pretty much everything we do is accessible in various formats. So if you are interested in 3D printing or the virtual reality or any of that, please let me know. Actually, I did want to just mention quickly that we are working with Framingham State University's Planetarium in order to do a version of this type of story, though more eloquent, for Planetarium. So if anybody's interested in talking about that, I would actually love to hear your perspective on what would be useful in doing that kind of translation, what formats would be best, that if you have any tips or tricks, I think I'd be really happy to hear them. But that's my story. The universe is yours, discover.
Don't sit down yet. Do we have any questions for our speaker this afternoon?
Did everyone get the whole cafe? Did it go around?
Oh, one of them made it through here.
Those are door prizes, right?
Definitely not. It takes like 2 days to print.
It's still making its way around. It's
Cool. Do you make the file for that available?
Yeah, so I have all the STL files for the 2 objects that I showed, and then we have a bunch of objects that we've been slowly adding to our collection. Those are all free for download. So go to the 3D print page, as that has all the files and like some basic instructions on what we did to print them, how long it took us to print them, that sort of stuff.
After you disclose that these images are created, and the public is skeptical of them, how do you bring them back?
Transparency. That is absolutely key. In all of the studies that we've done on cross-site development, images very clearly
Can you speak into the microphone, please?
So transparency is the answer there. Being able to state very succinctly, and you don't need to, write an essay on it, that what you did to the image and why is very, very helpful. That usually brings the trust level back up pretty quickly. That said, with the internet these days, there are some users who, will never gain trust again. But there's also like flat earthers. So except for what it's like, yeah. Any other questions?
Yeah, since I noticed you made some stuff in VR, have you done anything to make dome masters so that it can be display in the dome?
Not yet, though I would really like to. So have we done anything special with the VR for domes? No, we haven't yet. I do not have any dome skills myself. Hopefully, maybe we can work with Frank. Frank, I know, is an expert in that. To do versions of that eventually. I should say, one of the things that I found after we made the virtual reality version of SBA is that I almost felt like we had taken a step back in a way as far as accessibility. Because I went from a 3D print that was very accessible to a virtual reality thing that is no longer accessible. So one of the projects that we're working on now is how do you bring accessibility to virtual reality. It's a really important factor for people who are working on government funding. You have to be 508 accessible, ADA compliant. So what we're trying to do now is include variations of data sonification so that the data can be heard as you're going through the virtual reality space. That's kind of our next version. And also adding haptic technology, so we're able to essentially feel a rumble map, vibrations, as you're moving through the space, so that it's a true sight, sound, touch type of application. So that would essentially take it back to being 100% ADA compliant and 5A accessible. Those are kind of my goals. So I've definitely got bit by the VR bug. And I hope that we can just kind of keep working to make it better, because it's not great yet, but we're hoping to improve on it.
I guess I would just like to echo Sean's inquiry. The people that come to see us are the people that want to see all this great stuff. So whatever efforts you can make to make dome masters, which the format we're used to receiving material in, would be much appreciated.
Yeah, great. He's like, I'm just sitting in the corner minding my own business. Okay. And what I have been actually doing, I've had a bunch of planetarium events, and I take with me my Oculus Rift and my Google Cardboards, and it makes an excellent before you go into the dome experience or after you come out experience as a way to extend the information. So I've been providing like these tours on Cafe and the new one that we're working on now, which is Supernova 1987A. And another one, which is on the Galactic Center, having these virtual reality experiences available in addition for Google Cardboard, which is pretty cheap, and Oculus Rift. And we just tested it on HTC Vive, which it worked on that too. So, anyways, Frank.
If you'd like to make your VR more accessible, post it on YouTube and let people use an iPad.
We have YouTube versions, yeah.
Yes, well, the point is that the YouTube app allows you to use that as a window into your 3D thing. And we've been using that in Space Telescope recently, and it really works very well. a lot of folks in this conference got to see it.
Yeah, we do the YouTube version as well. It does give you some sense of being able to move around in the virtual space. But it's definitely a step removed from when you're actually immersed in the space, and that's what I think what we're trying to deliver. But yeah, I think the big point about virtual reality is accessibility. You can't just assume people are going to have their own personal virtual reality cave to walk into. So by having a sort of scaffolded approach to it, whether it's Oculus or HTC Vive, whether it's Google Cardboard, whether it's YouTube, we typically have all of those versions available for that exact reason. It makes it accessible to people whether they're in an under-resourced area, underserved area, or what have you, geographically spread out area, and there's a lot of different things there. Yeah.
This is very exciting because Cygnus X1, the black hole candidate, we can tell children and students, it's like, it's over in this area, and you show them Chandra's conception would be a lot more visceral if it was 3D or something.
Yeah, I will say that we've had a lot of success testing this out with students. Middle-aged kids particularly they're very video game savvy typically. So being able to offer something that's in an environment that they're already familiar with has been, I think, really great. Although we've done just a few levels of evaluation on the virtual reality project so far, and they've been very, very positive, particularly with younger audiences. So I'm really excited about that. Yeah.
Have you done anything to show audiences what it is that resulted in this? I mean, the star-going supernova, and
Yeah.
they ask, where did this come from?
Oh yeah, of course.
Yeah.
So I mean, I don't do that talk for you guys because you
Yeah.
know, but yeah, we always start. We actually have been fitting the Cassidy A object specifically in the story of stellar evolution as a whole. My dream, if you will, is to do kind of a virtual reality journey through stellar evolution by using some of these data-driven objects that we have. I have a colleague who's working on a really cool aspect of a 3D sun that changes over time. And that's a great place to start, because you start with your own star and what it will not be, right? And that tells its own story. But I think that there's a couple things. One, the technology is pretty new, so I don't know how many resources we really have to devote for my big dreams. But also, it just takes a lot of time to do. So it's something that telling the context of it is really important, which I do when I start with non-expert audience. Yeah.
Perfect. Just on behalf of Matt, we have a small gift for you for being our speaker today.
Oh, wow. Boy, this is really nice. Thank you. I don't usually get anything. This is cool.
Never just like Kimberly again.
Yeah.